Okay, so this is the outline of, not a chapter, so but the supplementary math for the circuit stuff. And actually, this kind of knowledge is really useful for engineering students, not only for Triple E or ECE student, but also will be useful for almost all the engineering students. So this is the outline. So first, I'll try to explain what is differential equations. How does it differ from the algebraic equations that you know really well, I suppose. And then inside the differential equation, we have different types of classification. So one type is to say whether the equation or whether the system that this differential equation is linear or non-linear. Okay, and then going to a very specific type of the linear equation is that this is constant coefficient linear ODE. Okay, so constant coefficient linear ODE. So also we come up with this ordinary. Okay, but I suppose when you first learn the calculus, starting from the single variable calculus, all the stuff are ordinary, okay? Unless you have learned the multivariable calculus, then you will facing something like partial derivative or partial differential equation. Okay, so anyway, I will try to also talk about how to solve the constant coefficient linear ODE in 3 steps. Okay, because for other type of ODE, no matter whether it's linear or non-linear, those kind of differential equation are not necessary to be solvable by hand. Okay, sometimes you really need the computer-aided program to solve the numerical results. But for this specific type, constant coefficient linear ODE, we have a well-developed system to really solve this kind of differential equation, no matter the equation is second order, third order, or so on. But of course, usually when we try to calculate by hand, usually it should be like first order or second order, or maybe at most third order. Maybe sometimes it's solvable, but usually we will not try to make the order too high. Okay, anyway. So first, what is differential equations? Okay, so here it says in mathematics, a differential equation is an equation that relates one or more functions and their derivatives. Okay, so it consists of functions, it consists of derivatives. Okay, so because you have differentiation, okay, differential, okay, differential or derivative. Okay, so it should consider of some functions or derivative. Okay, so actually in high school or even in primary school, what you always solve is like an algebraic equation. Okay, algebraic equation. Okay, which is like let's say 2x plus 1 equals 7. Okay, so actually, I think all of you should be able to solve this kind of algebraic equation. This is only a first order with first unknown equation. So even a primary student should be able to solve it. The solution will be like moving 1 to the right side, and then it will be 7 minus 1 to be 6, and then 6 over 2 is 3. So it's extremely easy. And of course, in high school, you should have learned something more difficult, maybe like a quadratic equation, like ax squared plus bx plus c equals 0. So that maybe you can like factorize the quadratic polynomial to find the solution, or maybe using the general form like negative p plus or minus square root of b squared minus 4ac over 2a, something like that. So that's algebraic equation. So what is the difference? What is the difference between algebraic equation and a differential equation is that for the algebraic equation, the unknown is just a value. It's just a variable. Okay, it's just only a single value. Okay, so this is 3. For other algebraic equation, it can be 4. It can be 1 plus I. Okay, can be just a single real value or single complex value. Okay, it cannot be a function. But here, for this differential equation, the unknown is a function rather than a single value. So this makes things much more difficult to handle. Okay, so and then the first we will talk about ordinary differential equations. So ordinary differential is nothing but d, this d. Okay, so nothing but this d. Okay. So when you learn calculus, you have something like dy dx or dx dt, something like that, depending what is the independent variable. Okay, so in that case, a more rigorous definition can be like an equation contains only ordinary derivative. Ordinary derivative means for your function, you can have several functions, but for a single function or for even more functions, they only related to a single independent variable. Okay, so of one or more dependent variables with respect to a single independent variable. So this is the most important part, is you only have one single independent variable, which means that for this case, y is only the function of x, or maybe x and y are the function of t. Okay, of course they are different cases. Okay, so just 3 examples for you to consider. So for the case number 1, the unknown function is y, and then the independent variable is x. Okay, so this is something like y of x. Okay, y is a function of x. And then for the second case, the same. Okay, so you have an unknown function to be y, and then the single independent variable is x. You don't have other independent variable. Okay, and then for the third case. Okay, so for the third case is the second case, also this one, and then for the third case, x and y are also unknown function. And both of them are only a function of t. Okay, so this is x of t and also y of t are the unknown functions. Okay. Okay, so as much as it has the ordinary differentiation or ordinary derivative, they are called ordinary differential equation. If for some of the case a function has multiple independent variable, just like in chapter 24, okay, when we learn e to be negative v, okay, negative gradient of v. Okay, so in that case, actually, if we write it in a more complete way, it could be like x, y, z, okay, something like that. Okay, we don't expect it vary with time. Okay, and then v is also a function of x, y, z. Okay, so in that case, if we try to write only the x-axis component, ex will be like negative partial v x, y, z partial x, something like this. Okay, so which means that even though the potential can be a function of x, y, and z, when you try to take the partial derivative, which means that at that time you consider x is the only variable and then y, z to be constant when you try to calculate the partial derivative of a function with respect to x. Okay, of course you can also take the partial derivative ey to be the negative partial v x y partial v x y and z with respect to y. Okay, so at that time you consider y to be the only variable, only variable, and then xz to be a constant when you try to evaluate partial v, partial y. Okay, of course you can also write out ez to be the, but don't try to repeat again. So I think you should be able to understand what is ordinary differential equation and what is partial partial differential equation. Those are called the PDE. Okay, so the ordinary differential equation in short form is ODE. Okay, so here, after knowing what is ODE, so here we try to talk about what is linear differential equation. Okay, so here, for the first equation, we try to have an idea that x is the unknown function, and then t is the independent variable. Okay, and x in this case is called dependent variable. Okay, so yeah, so independent means 独立, and then dependent means 相依. Okay, so which means that t can be changed to different value, but x is not free to change to different values. It depends on t. Okay, so x is called dependent variable. It depends on t. Okay, so here x is the unknown, t is the independent variable. So in that case, all the linear differential equation can be written in this form. Okay, it's like a little bit abstract, but the idea here is that if we try to collect all the term with x to the left side, okay, so which means that this is f, okay. This is not a function, we call it a functional, okay, in Chinese called 泛函, which means it is a function of function. So originally, if it's like f of x is like a function of a variable, but here, functional means it is a function of function. Okay, so here, this is a functional. Okay, so inside it, all the input are different functions. Okay, so x is a function, dx dt is another function, up to dn x dt n is also a function. Okay, so inside this functional, okay, we have quite a lot of functions to be the input. Okay, which means that on the left side we only have the term x dx dt all the way up to the nth derivative of x with respect to time, but we cannot have something like x squared x times dx dt, the multiplication between any of them or the exponential of them or any other function of them. Let's say sine of x is not okay. Okay, so on the left side, okay, we only have all the first order of the function or the first order of the arbitrary derivative. Okay. So in that case, on the left side we will call this is a linear differential equation for the function x, and then for the right side, okay, so because we have already put all the x, all the terms including x to the left side, so on the right side it should only contain terms related to the independent variable, or maybe it's just a zero is okay. So of course zero is also a function of time, but on the right side it's only the function of the independent variable. Okay, so this is a general form of a linear differential equation. So why we need the linear? Okay, so here it says an nth order, this is called nth order, correspond to this nth order derivative, is said to be linear if the functional f is linear. Okay, so this is this is stupid. Okay, so the ODE is linear if the functional is also linear. Okay, but what does it mean? Okay, so and then here it can be written as we only have this thing. Okay, we only have this single term, just as what I mentioned. This is also this is the general form. It does not necessarily to be linear here. Okay, so this is general. Okay, this is a general form. Okay, so not necessarily to be linear. Yeah, it can be like have x squared or sine of x, something like that, make it not linear. But if it is linear, then the form should be like that. It only consists of single order of n derivative, n minus 1 derivative, all the way down to its original function. And then for the coefficient, okay, so the coefficient will be like the function of the independent variable, an of t, an minus 1 of t, all the way down to a sub 0 of t. Okay, so this is the left side, and the right side doesn't change. Okay, it can be an arbitrary function of time. Okay, so so for example, okay, it says y double prime, okay, which means it should be like y double prime will be the second derivative of y with respect to x, okay, or time, okay, so it depends on what it asks you, okay, so it can be second derivative, the first derivative, and then the original function. And then this one is the third derivative, and then this is the first derivative, and then this is the function of the independent variable, so this is okay. This is the original function, and then this is the function of time. Okay, so both of them are linear ODE. But for the bottom case, this is 1, 2, and 3. Okay, so for the first one, okay, this term is linear, but this one is not linear. Okay, minus x prime is not linear because this is the multiplication between the function and its derivative. Okay, so this one make it non-linear. Okay, this term make it non-linear. And then for the second case, this is okay, this is okay, this is okay, but this one is non-linear. Okay, so this one is non-linear. And then this one is the fourth derivative, okay, with a bracket, okay. The fourth is within the bracket means it is the fourth derivative. So this is okay, but this is a square, okay, so this is not okay. This is non-linear. Okay, so you can easily distinguish whether a differential equation is linear or not. Okay, so now we come to the part that why we need it to be linear, because linear is a very convenient property. Okay, even for most of the course in the bachelor study will be like to learn the characteristic of some of the linear systems. Okay, of course for me double E will be like linear circuit. Okay, for other department can be something like linear control system or whatever. Okay, so we need the linear system because it is calculatable, okay, with only hand, okay, especially with the tool of Fourier transform or Laplace transform, okay, Fourier transform, Laplace transform, okay. So I suppose you will have learned it later, but not in this course. So as much as we have some mathematical tool like Fourier transform, Laplace transform, we'll be able to solve different linear system easily. Okay, so in that case, here we try to talk about the linear property here. So here it says, in the previous case I just mentioned, okay, this is stupid because it's just tell you that okay, if the ODE is linear, if the functional is linear. So how about what does it mean for the functional is linear? So here it says, if the functional f or capital F is linear, means that it should satisfy this property. Okay, this property. Actually, this property include two parts. Okay, include two parts. The first part, we'll say it is actually called superposition. Okay, the first part we call it the superposition. Superposition. Okay, which means that if f, okay, suppose here if we have x of t to be x1 of t plus x2 of t, something like this. Okay, so we have two functions, okay, and then add it to another one. Okay, so here it says if f of x of t will be like equal to f of x1 of t plus f of x2 of t. Okay, which means that we can exchange the order, which means that this one could be like f of x1 of t plus x2 of t. Okay, original it is like this. This is always true because we have this condition, but we need it to be linear if this part is equal to that part. Okay, which means that here we add the two functions first and then take the functional. But here we take the functional first and then we add the results together. Okay. Okay, so it feels straightforward, yeah, because so it is like obeying the intuition, but actually we need this property, okay, one of this property to make the to make the calculation easier, yeah, because in the real world it is not necessarily like that, yeah, because suppose you buy something in the supermarket or maybe you buy something on the Taobao, okay, so probably sometimes maybe you for product A, okay, you pay $10 and then for product B you pay $20. Okay, of course you only buy one, you pay $10 for the first one and then pay $20 for the second one. But sometimes if you buy A and B together, maybe you only need to pay $28 rather than $30. Okay, you have some discounts, something like that. Okay, so in the real world, it is not necessary to be like this linear. Okay, especially when you're going to buy something. Okay, so in that case, if you buy two products with only using only $28, then in that case, buying, okay, the operation of buying is not linear, okay. So here, linear is important. It's actually part of it. And then the other part, we will also call it the homogeneous. Homogeneous, okay, homogeneous, okay. Okay, which means that if f of a times x of t, we will say it is equal to a times f of x plus x of t. Okay, so this is called a homogeneous. This is also straightforward. If you want to buy Coca-Cola, okay, one tin for let's say $5 for easy to calculate. Okay, if you buy two tin, okay, it costs you $10. Yeah, but if you try to buy a pack, okay, with 18, okay, it won't cost you $30. It costs you only 20-something dollars. So it is not linear either. Okay, so if you buy more, then you only need to pay less. So this is not homogeneous in that case. This is not linear in that case. Okay, and then by combining the superposition and then the homogeneous, we can write it as a single one. So because first, okay, we can try to apply the superposition to make it like f of a1 x1 t and then plus f of a2 x2 t. Okay, so we use the superposition to break these two functions into two parts, and then we try to take the functional first and then Later on, we apply the homogeneous property so that we can make it like A1F x1 of t plus A2F x2 of t. So this property is important for solving constant coefficient linear ODE. So hope you keep this in mind, okay? Although you won't try to apply it directly, but later on when I try to tell you the 3 steps to solve the constant coefficient linear ODE, if you can understand this property, then you may be able to understand it, why it would be like that. Okay, it is not a very rigorous proof. Okay, it's just like a procedure. Tell you need to follow the step A, step B, step C. Okay, and then after finishing these steps, then you have already solved the linear constant coefficient ODE. Yeah, so you need to slightly memorize the procedure, but yeah, only 3 steps is not that difficult to understand to memorize. Okay, so here we talk about the constant coefficient linear ODE. So which means that just now, when we talk about the linear ODE for all the coefficients can be function of time. Okay, in that case, this is not easy to solve yet. Okay, so in that case, if we have constant coefficient linear ODE, which means that all the coefficient in a linear ODE are constant, which means that an is just a constant, an minus 1 is just a constant, all the way down to a0 is just a constant. So on the left side, constant multiplied by the nth derivative, constant multiplied by the n minus 1 derivative, all the way down to a constant multiplied by the original function. Okay, it will be the left-hand side related to the unknown function part. And then on the right side, still g of t. So nothing special there. So this is called the nth order constant coefficient linear ODE. So this type of ODE is easy to solve. Maybe you say, oh, this is not easy at all, but this is solvable. Okay, it guarantee. Okay, if you follow the procedure, I'll talk about that later on. If you just follow the procedure, you don't need to think, okay, what is the method to solve this differential equation? Because for solving differential equation, there are many different methods to solve different kinds of differential equation. But for this specific part, namely the constant coefficient linear ODE, you just don't need to think anything, or you just apply the 3 steps, then you can solve the constant coefficient linear ODE. Okay, so that's why I say easy here, okay, to solve with a systematic procedure. Just need to follow the steps, then it will be done. Okay, so to solve a constant coefficient linear ODE like this, we should the first step, okay? So just like I mentioned, we have 3 steps, just like how you put an elephant in a refrigerator, okay? It's to open the door for the first step, and then put the elephant in for the second step, and then close the door for the third step. So it is just as easy as putting an elephant into a refrigerator. So here, solving the constant coefficient in ODE, the first step is to solve the homogeneous solution. The homogeneous solution means on the right side, it should be a function of time, but first we try to make it a 0. We try to make it a 0. Okay, so we try to solve this first. This will be easy to solve. And then for the second step, we try to solve the particular solution, which means that this part is related to the g of t, okay? And then for some specific type of function, we have already tells you how you should guess the form of the solution for the specific type of g of t, or the combination of them. Okay, and then for the third step, okay, you already have the homogeneous solution, you already have the particular solution, xc of t, xp of t. Then the final step is just to add them together to be the complete solution. Then this is pretty much it. So it will be pretty easy to remember. Okay, so first step, make the right hand side to be 0 and then solve it. The second step, according to the specific g of t or the combination of some specific function, you try to guess the solution correspond to the specific functions, and then you can be able to solve the undetermined coefficient for the particular solution. And then finally, you add them together. Then it will be the complete solution. Okay, finally, you should check the initial value. For some of the case, the problem may provide you some initial value. Okay, usually it will give you some initial value. So if you have some initial values, then you can just plug it in the solution and then to determine some unknown coefficient. Okay, because if we don't have the initial value to constrain the complete solution, then it can have arbitrary many solutions. It will have some unknown variables there. Then it will be the complete solution. But if you have some initial value, okay, a initial value or some initial value depending on the orders of the ODE, then you will be able to solve the unique solution, okay, to determine the unknown coefficient in the xc of t. Okay, so this is a very brief overview of how to solve the constant coefficient linear ODE. Okay, so maybe let me